So this is, once again, kind of a review of what we did in Chem 1 today. So we're giving you a simplified version of redox, because once again, Chem was simplified compared to what we have to do next class. In order to understand and identify whether or not a reaction is an oxidation-reduction reaction, and also identify what was oxidized in a reaction and what was reduced, we have to remember how to assign oxidation numbers. So on the top of that handout, there's a 1 through 8 that hopefully reminds you of how to assign oxidation numbers. For example, number 1, if an element is by itself, and that includes diatomics, it would have a 0 for an oxidation number. So my O2 up on the board would be given an oxidation number of 0. Again, oxidation numbers are meant to be kind of a loosely identification of number of electrons start to finish. Now it's kind of weird because oxygen doesn't have 0 electrons around it. Sometimes it takes into account charge if it's ionic. However, there's a lot of covalent things, and that's where things get a little bit trickier for us. Number 2, if it is an ionic, it's equal to its charge. For example, if it's an iron plus 2 charge, it'd be 2 for its oxidation number. Fluorine, being the most electronegative element on the periodic table, will have a -1 no matter what. Typically, your alkali metals are a +1, your alkaline earth metals are a +2. Hydrogen's usually a +1, unless it's bonded with a metal. It's a -1. It tells you typically oxygen's a -2, but there are a couple exceptions there. Rules 7 and 8, I think, are the important ones otherwise. Number 8, if I skip ahead, the oxidation number of an entire compound should be 0 if that compound had no charge. And then finally, the most electronegative element would have an oxidation number equal to its charge. That's why fluorine is always a -1, and oxygen is almost always a -2, except when it's bonded to fluorine or in a weird peroxide issue. So there are 2 examples on the bottom of this sheet that are the same that I have up on the smartboard here. If you are assigning oxidation numbers, which once again is our first goal, you look at the 3 elements in the KClO3. The potassium only has 1 option. It's an alkali metal. That's a +1. By and large, oxygen is only going to have 1 main option of a -2 because that's its charge. Again, there are 2 exceptions to that rule, one of which if it was a peroxide, which we will actually be working with peroxide later. H2O2 is hydrogen peroxide. That's where oxygen's actually a -1 instead. And then, like it says in this how-to sheet, if it was bonded to fluorine. So what you'd have to do then, and if you have your good periodic table, you can see that there's a lot of little oxidation number possibilities for chlorine. +1, +3, +5, +7, -1. Those are the most common. That's not to say that those are the only options, because there's other oxidation numbers out there. However, what you would do in this problem is if oxygen's a -2 and there's a 3 of them, I'd multiply that to say I have a total of a -6. Potassium is a +1. All of these oxidation numbers together must balance out to be 0. Therefore, chlorine in this first problem is a +5. Second problem on the bottom is a little bit trickier because it has 2 polyatomic ions. NH4 is a polyatomic ion with a +1 charge. NO3 is a polyatomic ion with a -1 charge. Sometimes it makes sense to figure it out per polyatomic ion. Hydrogen, unless it's bonded to a metal, and nitrogen isn't, is a +1 oxidation number. And because of that, with there being 4 of these, that nitrogen must be a -3, because -3 plus +4 would equal a +1. And if it's not a neutral compound, like the KClO3 altogether was, if it's an ion, it should equal the ion's charge. As for the NO3 part, oxygen's a -2. That's a -6 there. Little math should tell us that nitrogen has to be a +5. The bonding of nitrogen in ammonium is different than it is in nitrate. That's one of the reasons why it has different oxidation numbers for the two nitrogens there. Is this ringing a bell? Kind of? The backside is a few practice problems. How will you take a few minutes, see if you can assign oxidation numbers? And then we'll go into the, here's an equation, assign oxidation numbers, determine what's oxidized and what's reduced. So if we started off with just assigning oxidation numbers, now what we have to be able to do is look at a chemical equation and determine what was oxidized and what was reduced. And for us today, that's step number one. We got a pretty significant step next class where we're going to start writing out what we call half reactions. However, today is more of review what we did in Chem 1. Quick reminder, again, oxidation means you lose electrons. The second definition I have up there is kind of the old definition of why was it called oxidation, is when things gained an oxygen through a chemical reaction, they were oxidized. Reduced means you gain electrons. Again, a lot of people don't like reduce with gaining electrons. They don't like those two, reduce and gain, coming together. However, the old definition was something that lost or reduced its number of oxygens. And what you'll see is actually the reduction term is kind of nice, because start to finish in a chemical reaction, if your oxidation number got smaller, if your oxidation number was reduced, you were reduced. If your oxidation number gets bigger, you are oxidized. So again, the second definition for each, you don't need to know that at all, but you do need to remember that oxidation means a loss of electrons. Reduction is a gaining of electrons. Grant, did I have you second semester when we had Chem and we did this? No, so then you might not know this next thing that I'm giving you, which is Leo goes Gur. This is how you can remember lose electrons, oxidize, gain electrons, reduced. Now, what if you take AP Bio? Is Kirker going to tell you something silly like oil rig? Oxidation is losing, reduction is gaining. She's a biology teacher trying to teach chemistry. Why would you take her word for it? You don't see me up here talking about RNA transcriptase and stuff like that. RNA or maybe DNA transcriptase? I don't remember. Remember, you have to have both occur. I don't know if you have to write down this last part at all. You can't have something lose electrons without something else gaining electrons. Okay, now my next slide is actually something that the College Board this year said, and it's on your sheet for today, that this term isn't one that is going to be used by them. However, they did not tell the people that made textbooks this for all the past years. So every textbook is still going to use this term that I'm going to show you on the next slide. So that's why I'm going to make sure that we're still kind of aware of it. However, I'm going to do my best on an assessment not to bring up what's called either an oxidizing agent or a reducing agent. So that's why I put an asterisk next to this, that this is not going to be on an assessment. Your goal sheet even says that goes beyond the scope of this. If you're oxidized, you lose electrons. If you read in a textbook something referred to an oxidizing agent, it's the thing that takes away electrons from something else. So it's kind of the exact opposite. But in a way, doesn't that make sense? If you're an agent, you are forcing something else to do this. So if you're an oxidizing agent, you are actually being reduced because you are taking electrons, forcing something else to lose. Reducing agents, that same type of thing as well, where if you're a reducing agent, you're the thing being oxidized. And I bring this up because our textbook will still use these terms. However, the College Board says they are going to try to avoid that. In particular, second semester, when we get into electrochemistry, you're going to see reducing agent brought up. It's going to be on a big table that we're going to be looking at all the time. Probably the simplest, most common example of an oxidation reduction reaction is the one I have up on the board. This is the equation for rust. Iron plus oxygen makes iron 3 oxide. It is expected of you to be able to assign oxidation numbers and then determine what was oxidized and what was reduced. So for example, iron would have a 0 oxidation number because it's by itself. Same with oxygen. On the product side, however, the oxygen would be a -2. The iron would be a +3. So if iron goes from a 0 to a +3, its oxidation number got bigger. Therefore, it was oxidized. If oxygen went from a 0 to a -2, its oxidation number got smaller. It was reduced. Now, if we were using the agent vocabulary, we'd say that iron is oxidized, so it's the reducing agent. Keep in mind, if you see things like polyatomic ions on both sides of the equation, like a nitrate on both sides, why even bother looking at the oxidation numbers for it? It's probably a spectator ion. Just look at the things that are actually going to change. There is a possibility that you could have more than one thing being oxidized and more than one thing being reduced, but typically you have one thing oxidized and one thing reduced. That gives us